Hello class, in this video we're going to be looking at transition matrices and its applications. The learning intention of this video is for us to develop an understanding of what transition matrices are and for us to learn how to solve application questions involving transition matrices. Transition diagrams and transition matrices can be used in probabilities where these probabilities are expressed as decimals so that we can model situations where there is a transition from one state or one condition to the next. So this is a very straightforward transition diagram over here, and what you're often asked is to translate this into a transition matrix, okay? When you're constructing your transition matrix, often the columns represent the current values, so the initial values, and the values on the sides of the rows, in this case, represent the future values. So in this case, I'm just going to start to fill in these values, and the way that we should do this is by looking at these values over here. So that just means that A is going to A. So starting from A and then going back to A. So therefore, I'm going to put a 0.7 over there, or 70%, and I'm going to put 60% or 0.6 where B is aligned together. Now what I'm going to do now is I'm going to refer to the diagram to fill in the other values. So therefore, going from A and then moving to B, that's going to be 0.3. So that goes there. And lastly, starting from B and moving to A, that's going to be 0.4. So I'm going to put that value here. Another feature of a transition matrix is that the sum of all the probabilities in each column will always equal to 1. And this is a nice handy thing to keep in mind when you're checking over your answers. Let's now look at another example which involves a 3 by 3 matrix. Again, you want to start off with the vertices where it kind of loops at itself. So in this case, starting from A and going back to A is going to be 20%. So I'm going to write 0.2. Starting from B going to B is 50%. And starting from C and going back to C is 40%. Now, just referring to the diagrams, you just simply need to put the values in. So starting from A and going to B is going to be 30%. So I'm going to write 0.3. Starting at A and going to C is 50%. So I'm going to put 0.5 there. Starting from B and then going to A, that's going to be 40%. Starting from B and then going to C, that's going to be 10%. Starting from C and then going to A, that's going to be 10%. And lastly, starting from C and going to B is going to be 50%. And similarly, you can check your answers by adding up all the values down the column, and they should all equal to 1. What I'd like you to do now is like you to have a go at answering a few questions. So have a go with this question over here. If you answer this question correctly, this is what your answer should have looked like. Have a go with another question. In this question, it says that 40% of the carriages that started at north ended up at the south depot. So therefore, I'm going to write 0.4 over here because it starts from north and ends up at the south. And it also says that 25% of the carriages that started at the south ends up at north. So I'm going to write 0.25 here. It doesn't give us the other values, but remember, all the values in the column needs to add up to 1. As a result, this value can be found by going 1 minus 0.4, so therefore that's going to be 0.6, and 1 minus 0.25 is equal to 0.75. Have a go with the next question. The next question wants you to interpret what does the element 0.65 represent in the matrix. In this particular question, 0.65 is over here, and notice over here it's saying that it starts off with a fine weather, but there's a 65% chance that's going to rain the next day, so therefore the correct answer is going to be B. The next thing that we'll be looking at are initial state matrices. An initial state matrix is a column matrix that shows you the starting information or the starting values for the changing situation. This is represented by the symbol S0, and there will be questions where this is actually given to you, but in other times you may need to identify what is the initial state matrix from the given passage. Let's look at an example down below. In this example, it reads, a large population of mutton birds migrate each year to a remote island to nest and breed. There are 4 nesting sites, and researchers suggest that the following matrix can be used to predict the number of mutton birds nesting at each of the 4 sites in subsequent years. In this particular question, it wants you to find out what is the initial state matrix given that there were 2,800 mutton birds at site C. So in this particular case, we need to construct a column matrix. Because our transition matrix is a 4 by 4 matrix, therefore our column matrix is going to be a 4 by 1 to create that column matrix. And in this particular scenario, they don't give us what the quantities are for site A, site B, site D, so therefore we're going to assume 0. Therefore, this is going to be my answer over here. Let's look at another example. In this example, it reads, in Melbourne, there are 2 major daily newspapers, The Age and The Herald Sun. Readers are fairly loyal to the newspapers they intend to buy. Records in a particular country town have shown that of the people who purchase a newspaper every day, 90% of people who buy The Age on one day will buy it the next day, and 80% of people who buy The Herald Sun on one day will buy it the next day. Suppose there are a certain day, 600 copies of The Age are sold and 1,000 copies of The Herald Sun are sold. The question wants us to both construct a transition matrix as well as the initial state matrix. So in this particular question, there are like two variables. So therefore, we're going to construct a 2 by 2 matrix like this. And now I'm going to put the values in. In this question, it says that 90% of the people who buy The Age on one day will buy the next day. So therefore, I'm going to put 0.9 in this case at this particular position over here. And I'm going to put 80% or 0.8 at this particular position over here. To find out the other values, I'm simply just going to do a subtraction. So 1 subtracted 0.9 is going to be 0.1, and 1 minus 0.8 is going to be 0.2. So that's what our transition matrix should look like. To create our initial state matrix, it needs to be a column matrix, so therefore it's going to have an order of 2 by 1. And in the paragraph, it says 600 copies of The Age were sold and 1,000 copies of The Herald Sun are sold. So I'm going to put 600 and then 1,000 down below. The next thing that we're looking at is matrix recurrence relations. So when we're trying to find out what is the next state or the next condition of a system, this can be found when you multiply the transition matrix by the current state. Each state depends on the previous state, and this can be represented by the following matrix recurrence relation. So there are two formulas that you could use, but the way that our textbook uses is in this particular format, but sometimes in some trial exams, you may encounter it in this particular format over here. Both mean the same thing, because if you look at both of these equations, it's saying that in order to find out the next value, you need to know the current or the previous value before that, okay? So therefore, if you're trying to find out what is S1, the next state or the next condition after the initial state, this can be found by going S1 equals to transition matrix multiplied by the initial state. S2 could be found by going S2 equals T times S1 and so forth. And the reason why this is referred to as the matrix recurrence relation, because that you need to constantly repeat and multiply by the previous term to get the next term in the actual sequence, okay? Let's look at a couple of examples. In the first example, it says that the factory has a large number of machines, and these machines can be in one or two states, operating or broken. Broken machines are repaired and come back into operation and vice versa. At the start, 80 machines are operating and 20 are broken. So that tells us essentially our initial state matrix. Use the recurrence relation down below where they've given us this over here as well as our transition matrix. The question ultimately wants us to find out what is the number of operational and broken machines after 1 day and after 3 days. To find out the number of operational and broken cars, essentially what we need to do is find out the value of S1. So S1, remember, can be found by going transition matrix multiplied by the initial state. So if you're going to chuck all these values into the CAS calculator, this is the answer that you should be getting. Ideally, in order for you to get full marks, then you need to write a sentence to state how many operational and broken machines there are after 1 day. So in this particular case over here, there's going to be 69 operational machines and 31 broken machines after 1 day. However, because I don't have enough space, I haven't actually done so, but make sure that you guys do this, okay? In order for us to find out how many operational and broken machines there are after 3 days, we need to do this using a recurrence relation, meaning that you need to find out what is S2 first in order for you to find out the values of S3. So to find out S2, you need to multiply the transition matrix by S1. So if you put this into the CAS calculator, this will be the value of S2. So S3 can be found by multiplying the transition matrix by S2. And if you put this into the CAS calculator, this is going to be our answer. To ultimately answer this question, again, you need to write down a written statement. So because these values over here are not nice whole numbers, we're going to need to round these values accordingly. So in this particular case, you would need to answer by saying that there's going to be 53 operational machines and there are 47 broken machines after 3 days. Let's now look at another example. In this example, it reads that there's a cluster of 3 islands and it's inhabited by people who readily move from one of these islands to another. Some of the people move away from the islands altogether. This information is represented in the transition matrix below. The number of people on each of the islands at the beginning of 2016 is given by the following matrix, and it wants us to find out the values of S 2017. So to find out what is the next state, remember, all we simply need to do is multiply the transition matrix by the previous state, okay? So therefore, if I multiply these two values using my CAS calculator, this is going to be my answer over here. The next part of this question wants us to now use the recurrence relations formula to find out what is the expected number of people on island B at the beginning of 2020. In the previous question, we've already found out what was the value of S 2017, and ultimately, we need to answer this question by finding out the values of S 2018, S 2019, and then S 2020. So therefore, S 2018 can be found by multiplying the transition matrix with S 2017, put this into the calculator, this will be our answer. Using this answer, we could therefore find out the value of S 2019, so therefore transition matrix multiplied by this matrix here will give us the value of S 2019, and lastly, to find out the value of S 2020, this can be found by multiplying the transition matrix with S 2019, and therefore you will arrive to this answer over here. However, the question wants us to find out what is the expected number of people on island B. So this value over here corresponds to the number of people found in island B, but because we're dealing with people, we need to round it to the nearest whole number, so therefore we're going to round it to 193 people. As you can see, using recurrence relations can be a bit tedious and time consuming, so there is another quick way for us to obtain the answer, and this can be found by using the following rule. To find out what is the state of the matrix at any time, what we need to do is we need to raise the power of our transition matrix to the power of n, where n could be 4 years, 5 years, 10 years, and then multiply that by our initial state matrix. So let's look at the example that we just looked at earlier on to see how this rule actually works. So the question wants us to find out what is the value of S 2020, essentially. So in this case, from S 2016 to S 2020, that's a difference of 4 years. So what I'm going to do is therefore raise to the power of 4 for my transition matrix and then multiply that by my initial state matrix. So therefore, if I raise it to the power of 4 and multiply by S 2016, again, you're going to see that it will arrive to the exact same answer. So therefore, our answer is going to be 193 people on island B. As you can see, this method is a lot more effective, but please note, you should only use this method if it doesn't actually give you the recurrence relations. If the question has already given you the general formula of the recurrence relations, then you're going to need to do it step by step individually. What I'd like you to do now is to answer a few questions. In this question, I want you to construct a transition matrix as well as finding the initial state matrix. In this question, there's a 65 chance for customers to shop at A to shop at market A the next day. So therefore, I'm going to put 0.65 over here, and I'm going to put 0.82 down over here because customers who shop at shop B will move on to shop B the next day. To find out the other values, I subtract it from 1. So therefore, 0.35 goes here and 0.18 goes over here. To find out my initial state matrix, which is denoted by S0 in this case over here, it says that there's initially 7,500 people at market A and 2,500, so I'm going to put these values like so. Part B of this question wants us to use the recurrence relations to calculate the number of people shopping each market on day 2. So in this question, we need to first find out the values of S1, so then we can find out the values of S2. So S1 can be found by multiplying the transition matrix by S0, and if you do this on the calculator, this is going to be our answer over here. Now that we've got this answer, we can now find out the values of S2. So remember, S2 can be found by multiplying the transition matrix by S1. So if you do that, you will arrive to this answer. And now we need to write our answer as a worded statement. But keep in mind, we do need to round these values accordingly to the nearest whole number. So I'm going to say that there's going to be 4,303 customers at shop A, and there's going to be 5,697 customers at shop B. Part C of this question wants us to calculate the number of people shopping at each market on day 10. So in this question over here, notice that it doesn't actually ask us to use the recurrence relationship at all. So therefore, we could use the explicit shortcut rule. So if you may recall, the rule was Sn is equal to t to the power of n multiplied by S0. So therefore, if I'm trying to find out S10, I'll put the value of n as 10 and multiply this by my initial state matrix. Therefore, you'll get to this answer over here. And now, similarly, we need to round these values to the nearest whole number. And therefore, you'd say there's going to be 3,398 customers at shop A and 6,602 customers at shop B on day 10. The next part of this video is for us to look at steady state. So the steady state occurs when the numbers in the state matrix no longer change between time periods. In order for us to find out what is the steady state, we need to choose a large number for n and calculate n as well as n plus 1 to show that the state matrix does not change between those 2 years, okay? And ideally, I like to use the value of n equals to 50, but ultimately you could also use n equals to 100 as well. So let's use this example over here. So I'm not going to read this question with you at all, but ultimately it wants us to find out what is the long-term probability. In other words, what is the steady state, okay? And he also tells us that the initial day is going to be wet. So therefore, if you were to write down what is the initial state matrix, it's going to be written as 0, 1, 0 because it's saying that it is dry, and 1 over here represents that it's wet on the first day. So please recall that we're going to be using this formula, and as I've stated earlier on, we're going to use the value n is equal to 50 as well as n is equal to 51, so the one just above that, okay, to prove that these states do not change over time at all. So therefore, if you plug in these values accordingly, you're going to get to the exact same answer, and as a result, this proves that this has now reached steady state, where these values no longer change whatsoever. Therefore, to now answer this question, the probability of it raining, given that the first day is going to be wet, is going to be equal to 47%. Let's now look at another example. In this example, this was taken from the VCAT 2018 exam paper 1, and in this question it reads, a public library organized 500 of its members into 5 categories, and there's a transition matrix down below which shows you the number of books borrowed per month by the members that it's expected to change from month to month. And ultimately, it says in the long term, which category is expected to have approximately 96 members each month. So in this case over here, because it says long term, the question ultimately wants you to find out what is the steady state solution. In order for us to find out what is a steady state matrix, we need to raise the power of our transition matrix to the power of 50 or 100 or whatever it is, and then we multiply that by the initial state matrix. However, if you read this question carefully, it doesn't actually tell you what are the exact quantities for our initial state matrix. What is the value of S0 or S0 in this case? However, it actually doesn't matter at all, but as long as it meets this condition, then you will be able to arrive to the same answer. The reason why we could use any values for our S0 is because remember that the definition of a steady state is that over time it will eventually arrive to this exact value. So it doesn't actually matter what our initial values are, because in the long term they'll all change and arrive to a fixed number. So in this particular case over here, I could use the values of J, K, L, M, and N as 100 each, as altogether this will add up to 500. So if I was to find out my steady state for S50 as well as S51, notice that these values do not change whatsoever. So therefore, our answer is going to be K in this case, category K. Now to prove that we could use any values for our initial state matrix, this time around I'm going to adjust these values so that you can see that the original values don't matter as long as the total adds up to be the same. So this time around I've changed the values as you can see over here, and again I've raised it to the power of 50 and 51, so that should be 51 there, and notice again you arrive to the exact same answer. The last part of this lesson is for us to learn about the state matrix that involves culling and restocking. We are now going to be looking at situations where we're going to either remove stuff, which is known as culling, or adding stuff into the system, which is referred to as restocking. Since we're either removing or introducing a constant amount of stuff, the recurrence relation has a plus B component to it, which is often represented by a column matrix. Since we are going to be constantly adding or removing stuff at each time period, this means that the total number of items in the actual system will change between each state or between each time period as well. This is completely different compared to the other recurrence relationship which we looked at previously, because in this particular relationship, the total amount remains unchanged over time. So what I'm going to do now is I'm going to show you an example so that you can see how the total amount changes over time when you've got culling or restocking. So in this particular example, we know that this involves either culling or restocking because it has a plus column matrix, okay? So you're adding by another column matrix. And if you were to put this into the calculator, notice that this total amount has actually changed over time. We know that previously the total number of farm animals, let's say, was 90. But if you were to add up and find out the total of this value, it's now 94, okay? So as you can see, it has now changed over time. And if you wanted to find out what was the value of S2, again, you'd use the exact same formula where we go the transition matrix multiplied by S1 plus by the constant matrix B. And if you were to find out the answer using the CAS calculator, this will be our answer. Again, if I was to find out what is the total of this is going to be equal to 98. And as you can see, the total amount has increased by 4. One thing that I would like to point out is that there is going to be no shortcut way or rule where you can find out what is the value of S3, S4, S5, okay? So there is going to be no powers whatsoever that you're going to be raising it for our transition matrix. So what I mean by that is you're not going to be using this particular formula over here, okay? There's none of this formula when you've got culling or restocking. On this slide over here, I'm going to show you again the recurrence relationship, which does not involve culling or restocking whatsoever. We know that this doesn't involve culling or restocking because you're not adding by a column matrix. So if you were to find out what is S1, notice that the total amount over here is going to equal to 90, which is the same original amount what we started off with in our S0. Similarly, if you want to find out the value of S2, notice that the total amount doesn't change whatsoever. Let's now look at another example that involves culling and restocking. So in this particular question, it reads, a company wishes to start a commercial whiting breeding farm and it starts with 20,000 whiting eggs, 4,000 baby whiting and 500 adult whiting. The following could happen in a year. So eggs could die or they could live and become a baby whiting. The baby whiting could die or they could live and become an adult whiting. The adult whiting could die or they could live for a while but eventually die. So that's what E, B, A, and D represents. The first part of this question wants us to find the value of our column matrix, okay? And this can be found by reading this particular statement over here. So it's saying that 500 adult whiting each year is sold. So therefore, this value, the third value in our column matrix, should have a negative sign. And it's saying that we're adding an extra 200 baby whiting and we're also adding in an extra 8,000 eggs, okay? So therefore, if I was to write down my column matrix, this is what our column matrix should look like. For part B of the question, it wants us to find the number of adult whiting after 1 year. So therefore, I'm going to be using my recurrence relationship. To therefore find out what is the value of S1, we therefore need to multiply the transition matrix by the initial state matrix and add it by the column matrix. So therefore, if I put this into the CAS calculator, this is going to be my final answer. After I've found out the value of S1, I need to now interpret the values to finally answer this question. So the number of adult whiting after 1 year is therefore going to be equal to 1,200. Part C, we need to do the exact same thing again to find out the value of S2. So S2 can be found by going transition matrix multiplied by S1 plus B. So if you put that into the CAS calculator, you should get this as the answer. And therefore, the number of adult whiting after 2 years is going to be equal to 2,390. This is the end of the video. Hopefully this video has been informative. Thank you for watching and I'll see you guys again in the next one. Bye.